Hello and welcome back to differential equations. All right, the goal for today, 1.3 on slope fields. I will just remind you to please read Canvas announcements. I will be posting more stuff very soon, so make sure you are reading those, and office hours are posted and a whole bunch of stuff, so just make sure you are getting all of that stuff there. All right, so slope fields. If you have any questions, again, please write in the chat. Right, I am monitoring YouTube chat, so you can write questions there. So, where do we start? We talked about differential equations. We said what they are. We know that that's the equation which contains independent variable function and its derivatives. So we know a lot of stuff about differential equations. We can check them. We know that there are general and particular solutions. We know that we need that initial point to come up with a particular solution. Classify differential equations. So we did linear equations, and we talked about the linear equation, the first, second order, homogeneous versus non-homogeneous, that's if it's equal to 0 or not. So all of that stuff we did, and now we want to learn a method which will allow you to solve first order differential equations without solving first order differential equation. Graphic method, because you hopefully remember and understand that your differential equation contains the derivative, and derivative is a slope, the tangent line, right? So we can do a lot with that information. Now, let's consider equation y prime is equal to x plus 1. So we'll consider that equation. And in this equation, we are going to take a look at the solution using the method we know from before. So we're going to put this in the superior Leibniz notation. Instead of that noob prime over there, we're going to write dy over dx. And then we're going to write dy is equal to x plus 1 dx. This is us doing separational variable for a millionth time. Integrate both sides to get that y is equal to x squared over 2 plus x plus c. And we know that this is some kind of a parabola. I don't know where this parabola is exactly because of plus c. We can say if x is equal to 0, then y is equal to c. If x is equal to 1, right, we can figure things out, but we can just draw a whole bunch of these parabolas all over the place and say they're all x squared curves. And problem is solved, right? That's done. Now, what if you are not able to use separation of variables? What if you are not able to use any of the methods we are going to teach, right, and see in this class? I mean, learn in this class. You can run into equations that don't fit stuff that we are going to learn. We're going to learn exact equations, integrating factor, linear equations, separation of variables, right? We're going to have number of methods to solve these equations. What if the equation doesn't fit into any of them? Substitution method is another one, right? What then? So the method that I'm going to show is, which is the slope fields, is a very tedious and slow method, and we're going to do it on this problem to understand the way it's done, because we want an easy problem to learn on, and we better get answer of this form as we solve the problem. So let's take a look at the slope field approach. So the first thing we are going to understand here is that dy over dx is slope of the tangent line, which means that we are going to have these lines all over the place. So if I write dy dx, let me just box this off as stuff we did before. So if I have dy dx equals to x plus 1, this is the slope of the tangent line equals to this mess. So you can think of it as the m tangent equals x plus 1. And we can pick m tangent different values for it. Let's say from -2 to +2. And that will give us guides on well, we'll see what that gives us. You don't have to pick -2 to 2. You can pick any values. Sometimes, you know, might increments of e or pi or something. That depends on the problem and the situation you have. Currently, for this vanilla problem here, I'm going to pick -2 to 2. So we're going to start our journey. Now, first, before we do any calculations or anything, I need to draw XY coordinate system, because this is the one that will house everything I have. And now I'm going to pick m, which is dy dx, equals to -2. So I choose that, right? I pick that. And then when I plug that in, I'll get -2 is equal to x plus 1, from where I get the equation x equals -3. All right, so I got x equals -3. And I'm going to actually put this to be orange. Come on, pick orange. Thank you. All right, I have -3. Let's draw -3. So 1, 2, -3. We're going to draw this line. This line is x equals -3. And on that line, I'm going to put small tangent slopes of -2. So you can put those slopes anywhere. They don't have to be equally spaced or anything like that. It's just, right, OCD, if you do so, which is what I'm going to do. But you don't have to, right? So -2 slope would be, right, if you go corner to corner, that's -1, so -2 slope has to look like this. And I'm just going to go with the -2 slopes like that. It's important to be as OCD as you can as you draw this, because there is a distinction now, right? When we pick m equals dy dx equals -1, and you plug that in here, and you get x equals x plus 1, and let's go blue, you get x equals to negative 2. You see that now the slopes are negative 1 on the line x equals negative 2. So here's my line x equals negative 2. And now the slopes are a 1. Negative 1, sorry, negative 1. So these are at 45 degrees. So I have a line x equals negative 2. Those lines are called isoclines, and then you have these little slopes on it. So you pick the slope and you compute the line on which that slope lives on. Pick m equals dy dx to be 0 and plug that in. And solve it. And let's go purple now. It's going to be x equals negative 1. So, we have a line that it's negative 1, and the slopes need to be these horizontal little lines. So we'll just have this. And that's our line x equals negative 1 isocline with a little tangent slopes on it that are flat. All right. Pick m equals dy dx equals to 1, and we get 1 equal x plus 1. And let's stay in black. X equals 0. So now line x equals 0, which is our y-axis, gets the slopes of 1, which is 45 degrees. So it's getting these 45 degrees this way, right? They're trying to hit the corners of adjacent squares. So that's a 45 degree like that. And finally, pick m equals dy over dx equals to 2, which would be 2 equals x plus 1. And now let's go green, I guess. So x equals to 1. So now I'm going to have the line at 1. And that's x equals 1 isocline. And from there, you will have the, what do you call it? From there, you're going to have a slope of x equals 2, because that's the one you picked. See, m equals 2, slopes 2. So every slope that you pick, that you draw, will be the slope of 2. So that's more sloped than your slope of 1. So it's having a larger angle than 45 degrees. It goes up faster. Now I know it's not humanly possible to do this, exactly and perfectly without those, without instruments and things like that. But you are able to now make this what we call a field, directional field, which kind of gives you a guideline where the solution curve is gonna go, which way it's going to snake through this this slope field. So if I take now this, see, I have to, these guys will guide me to go this way, then this one bends, then this one is flat, then this one tells me right and goes up. And as you can see, as I draw these nicely and slowly, I'm getting these solution curves to be the parabolas that I was expecting earlier. Now, the beauty of this method is that you are not doing calculus. I don't know if that's beauty or not. You're not doing calculus here. You're not integrating. You're not solving any methods. You're doing a whole bunch of very busy work to come up with this slope field which guides your solution curves through. And if you have initial point, well, that initial point will be the physical point on the graph, and then the line that goes through that point will be your particular solution. The drawback of the system is that you're not getting an equation in terms of x and y and so on, right? So you can read, you're getting a picture. And then you have to pick the points from that picture and plug that into software to find the best fit curve and so on. So sure, if you are to pick points from a solution curve and plug them in the Excel, let's say, and do the best fit curve, or, you know, we have Mathematica and way better mathematical software than Excel, but Excel is easy to use. If you pick these points and you stuff them all in the, let's say, Excel, it will give you the best fit curve, which would end up being the solution that we had when we solved the problem without all of this tedious computation. So there you have it. It is a method that works all the time because you're always able to pick numbers and then compute the equation. And once you compute the equation, you draw that as the isocline, and then you put the little slopes on that isocline. And then later, you just need to snake your solution curves, be guided by these lines. Believe it or not, that's 1.3. There's not much to it once you understand how the whole procedure works. And you know, they give a lot of examples in a book. I'm flipping through it right now, and they show a lot of slope fields that go and follow these little slopes. So these little slopes guide the line as it comes through. So if I am to again draw another solution curve, it will have to follow these values and then come out to the other side. Now, obviously, you can go out more. You know, it's not just -2 to 2. You can use any values. Maybe you want to use -10, -5, 0, 5, and 10. Or maybe you don't need the negative part. So you're just going to use 0, 1, 2, 3, or 0, 10, 20, 30. Right? Depends on the scale of the problem, depends on the need and so on. This is a graphical approach to solving differential equation. Obviously, like every other graphical approach, it's going to take time, and it's going to take a lot of OCD to get this straight. If you are doing this on a lined paper that it's meant for you to write essays, not do math, obviously everything will be crooked and bad because you don't have proper spacing in X and Y direction. The only proper way to do that is to have the square paper like the grid that I have in the background, which I use all the time because all I do is math and physics, and that should not be done on the lined paper because you don't have the horizontal divisions, only vertical ones. So I'm going to now take a look at another concept that is the part of this lecture, and believe it or not, we're done. Now, this concept is very important concept because it is fundamental. The name is existence and uniqueness of solution. First off, you want to know that solution exists, and you also want to know that the solution is unique. Multiple solutions that are linearly independent are are not something that we are after, because that means that the uniqueness of the solution that we had so far in mathematics would be ruined for differential equations. And in some cases, much later on in mathematics, there is something that's happening for more complicated cases. But now that's something that we technically don't want. Now, we dealt with these situations before when we said, well, circle is not a function because 1x is is assigned to have two y's, and therefore equation of a circle is not a function because you can't have 1x produce multiple y's. Remember, x is an input that's supposed to produce the output, and function guarantees that an input produces a single output. So now for differential equations, we want to make sure that the differential equation that you put down produces exactly one answer, one solution. So one function is the answer for the differential equation. So it's the same concept, just a one skill up, right, level, one level up. You, instead of dealing with numbers, you're dealing with functions now. But it's the same principle. And for this one, you will need to know partial derivatives from Calc 3. And if you don't know partial derivatives from Calc 3, I'm going to ask you to either watch my YouTube lecture or anyone else's YouTube lecture, I don't care. It should, you know, if you're good with Calc 1 derivatives and the chain rule from Calc 1, you should be able to pick up very quickly the derivatives, the partial derivatives that are taught in Calc 3. I would say, 15 minutes or so, you should be good to go. All right, let's go with the theorem. So this is existence and uniqueness of solutions. Fit. Good. So the setup of the theorem is something that you have to check, and then conclusion of the theorem is that you have unique solution or not. So that's something you have to be careful with. So suppose that both the function f of xy and its partial derivative dy f of xy, those of you who took the Calc 3, I'll just put the df dy, you are used to this notation and you are also used to this notation. So I'll put all three notations. So suppose that both function and its partial derivative of y are continuous on some rectangle R continuous on some rectangle R. I'll have to explain that. Well, here is the explanation. In the plane, in the xy plane, that contains point AB in its interior. That's a large setup, but it's actually very simple. You have a portion of your whole xy plane, which is a rectangular portion. That's going to be a rectangular portion R, and you just have some point A through which this is point AB, through which the function is continuous, right? It goes through that point. That's all of this mess is just saying that plus the derivative of that one needs to be continuous as well. Now we'll deal with that when we get there. So there we go. Here is then. Theorems are always if. All of this is true, then for some open interval I, containing point A, so clearly now this interval I is on x-axis. The initial value problem dy dx equals f of xy with the initial condition of the point AB that we talked about, has one and only one solution. That is, well, or just on I. With that. And since it has it, that means it exists, and it says one and only one, meaning it's one of them. Done. So this is your definition, theorem, sorry. It might show up on your first exam, it might show up on the final as well. And now that's in a record here because it's all recorded live, right? This is the learning outcome of your course. You need to know this. This is one of the most important theorems as well, because if this wasn't true, then there would be no physics, which would mean no engineering, which would mean we still bang rocks to make fire, okay? So this is our life now, right here, this definition, and it requires you to check the partial derivative and make sure that the partial derivative exists, and then we're all good to go. So let's take a look at the an example of this, because we need to practice just a little bit of these partial derivatives and things. So let's go and say, how about problem 16? Says dy dx is equal to square root of x minus y, and y of 2 is equal to 1. Y of 2 is equal to 1. Now, what do I need? I need continuity, and I need continuous partial derivative in respect to y. And I need all of that at the point 2, 1. And if all of that is satisfied, we're good to go. So let's take a look. The first order of business is to say that my function f of xy, which is a multivariable function from Calc 3, is just square root of x minus y. And because we need to take the derivative, if it makes you happy, you can put the 1/2 power, or maybe you already know that it becomes 1 over 2 root, right? 2 root x or whatever. So now I want to find the partial derivative in respect to y. This is one of the 3 notations. Any notation is fine. You can use capital D of y, you can use this one, you can use the partial f partial y. So whatever makes you happy, because, right, your happiness is our primary concern here at ERNIC. So you go and you take this derivative by saying that this is going to be 2 square root of x minus y, and then the derivative of the inside in respect to y goes on top, which is -1. So this is your this is it, right? This is it. Now, if I want to discuss continuity of this problem, I'm going to first take a look at its domain real quick to see where is this function defined. Remember, we cannot take square root of a negative number. So when I'm looking at the domain, because clearly I'm not going to look for continuity and stuff, critical points and whatever else in calculus is there for the regions that are outside of the domain, right? That's just a waste of time. So you find the domain first, and then once you have the region pinned down, then you can take a look if your initial point is also part of that region. Because if this is a garbage point, right, which is not in the domain, we have nothing to work with here. There's no reason to work because, hey, the problem is not in the domain, right? It's not well defined. So go back and think about your problem. So domain is x minus y, and that needs to be larger or equal than 0, which means x larger or equal than y, so y lesser equal than x. And you can draw that and shade, because this is very easy. Domain, it's a 45-degree line through the origin, so there we go. And y needs to be smaller than x at all times. Well, that happens underneath the line. When I teach algebra, I say, okay, this is your Canada, this is your US, and then I'll figure out, do we shade Canada or do we shade US? And you can do that by picking a point. You can pick any point you want and just, take a look at the x and y values and see if it satisfies the equation or not. Let's say you pick this value here. This is 1, 2. Your x is 1, your y is 2. Your y is bigger, but you need a smaller y. That means we are shading United States, right? So that's your domain. You can quickly, check which way of the inequality. So we are shading this. Now, what is my point here? My point is x equals 2, y equals 1, and that is, here is the 2, 1 right here. Maybe I should make it red to stand out. There we go. So that's my point, right? 2, 1, and clearly it's in the domain, so it makes sense for us to look for derivatives and uniqueness and all of this kind of stuff, because the point is in the domain, right? All right, so continuity, right? We go back to calculus 1. You had in section 2.6, I actually just taught this, so I'm just going to flip this to calc 1 and remind you of the continuity theorems that you needed in calc 2 and now you need in differential equations. Here it is. So following functions are all globally continuous on their domain. And the first one listed is a polynomial. And then here, number 4, radical, right? So these are the two. Because remember, you have x minus y, or y, whatever, under the radical. So this is a polynomial in respect to x. This is a polynomial in respect to y. And by the line number 1, both of those are continuous because they're both polynomials. Now, the next theorem here in purple says that combinations and compositions of continuous functions are continuous. Well, here is the combination of minus. I combine two continuous functions with the minus. I still get a continuous function. And it also says that function composition is continuous. Now look at it. Don't you have a function composition of two polynomials stuck into or stuffed into the square root? So that's a function composition. So when you put all of these concepts together, you will say polynomials are continuous. Their difference, there we go, subtraction, right? Difference is continuous. And then composition of that polynomial with the radical function is also creating a continuous function. So yes, the whole thing over here is continuous. And now we know that the function is continuous. Now go back to our differential equation. There we go. So we just used Calc 1 over here to say, yes, it is continuous. Now we have this one. Now we know that we are not allowed to have 0 in denominator, and you are going to get that when x is equal to y, which is going to knock off the equal sign here. Now, what is the equal sign going to knock off? It's going to knock off this line and create that to be this dashed line, meaning that our domain now is smaller for this line because this x minus y is in the denominator, and that would create a 0. But this point that we are interested in is still not on that line, so no harm done. It is still in the region that it's continuous. It's still in the domain. So we're still good. So yes. And by the way, all of the rules that we talked about, the polynomials, the function composition, then this is composed into the function 1 over x, which is a rational function. The denominator is different than 0, right? So all of that stuff that we talked about earlier in Calc 1 still works here. You just have an extra step because you now have to feed this radical function into a rational function and just say that the denominator is not 0 because the point that we are interested in is not on the line. So this one is also continuous. And now let's go. So what have I done? I have picked this into a function. I have found the partial derivative for it. I have used the domain over here to make sure that all of the stuff fits in. So let's see if we ticked off everything that we needed to tick off from the if part so that we can make the conclusion and solve the problem. So suppose that both function and the derivative are continuous, and they are. We show that in the xy plane. It is in an xy plane which contains the point 8b. So AB is contained inside. Remember, 2, 1 is well inside the domain here. It's not on the dotted line or outside or anything like that. Then for some open interval, well, we're done. So that was it. If you know the theorem, if you know how to check continuity, I should have showed continuity for the Calc 3 function, but really Calc 3 or Calc 1 is no difference. It's the same stuff. It's just Calc 3 has more dimensions to it, but the same functions are still equally continuous. So we have all of that stuff, and that's it. That's all we get. If you found this simple and you're thinking when is the harder stuff going to start, you'll have to wait a little bit longer because this is 1.3, believe it or not. The homework will be available for you. We're going to take a break and then go into a much longer lecture, which we might or might not end today. And yeah, it is on separation of variables, but we are going to talk about more interesting problems than the population problem. And this is where we are going to develop the logistics function, which we are going to use in population problems later. So that will take some calculation. So go stretch your legs, sharpen your pencils or two, because you'll need them, trust me. And we'll be back at 11:50 with a new stream, same channel, same everything, obviously, I'm going to shut this one down because I have to switch the title. So I'm going to turn off the stream, and at 11:50 there will be a new stream with a new title. See you all in 5.